Jai Hind. The today topic is page replacement algorithm. This particular unit is covered under unit 4 of the subject operating system. So basically what we are going to discuss today, page replacement algorithms. So before going into the detail of the page replacement algorithm, first I will give an overview of the paging, and then I will relate the page replacement algorithm concept with this. As we are aware, but in the virtual memory, basically what we are doing, we are separating the user logical address space with the physical address space. So what it implies that only the part of the program which is under the execution, because when we are aware that when a program executes, only a particular instruction got executed, and it is using a particular maybe using a particular shared resource or file to complete its execution, and all other code we are not executing, but it is still in the memory, as we have seen in the concept of a paging concept, where we are required that the process, it need to be in memory when it is under the execution. But in the case of the virtual memory, what is happening, only the set of instruction or that page which is containing the instruction which is going to be executed, only that page reside in the memory. So only the part of the program need to be in the memory for execution, and it is also known as the resident set of the process. Logical address space can therefore be much larger than the physical address space, because in this what is happening, that for example, if I am having a 256 KB RAM, then earlier the case is that my process size is going to be fixed, which is equal to my RAM size. But with the virtual memory, what is happening, I can have a process size much larger than my RAM size, because now only a subset of pages, they are coming into the memory, and we are running only those instructions which are residing in those pages. But what happens if I require a page which is not in the physical memory, that is your RAM? Then in that case, what is happening, we need to bring that page from the backing store, that is a virtual memory which we are calling, into the your main memory, and only then we are able to execute the instructions which are residing on those pages. It allows the address space to be shared by several processes, and it is allow for more efficient process creation, because earlier if my process requirement is 5 pages, then I need 5 pages in my main memory to be there, so that my process can start its execution. If I am not having enough pages, that is 5 pages, then my process can't go for the execution. But with the virtual memory, what is happening, if I am having 2 or 3 pages in the memory, still I can start the execution of the process. I will bring only 2 or 3 pages into the memory. I will start its execution, and if I require some other page which is not present in the physical memory, then I will go to the backing store, bring that page into the memory, free some frames. I need some free frames in the RAM, so I need to free those one of the free frames, and I will bring that page from the backing store into the main memory, and we can start its execution. So it allows for a more efficient process creation in this case. Virtual memory can be implemented via demand paging and demand segmentation, as we have seen in the earlier concept, that is we are having paging and segmentation over there. That is, we are dividing the logical space into pages in the case of the paging, and the physical address, that is your main memory, into frames, and we are allocating the frames to the pages. Whereas in the case of the segmentation, what we have seen that the logical space, instead of dividing the logical space of the process into fixed parts, what we are doing, we are not dividing into fixed parts, but in unequal part. And these unequal, how we are defining this inequality, We are defining this according to the logic of my process, because when I go for a process, we are aware it may contain files, it may contain stack, it may contain tables, etc. So in that case, we can allocate, and all these segments are of different size. So instead of dividing the process into equal parts, what we are doing, we are dividing the process on the basis of this of its behavior. And once the segments are being generated, we are allocating the RAM, that is a physical memory, to these segments instead of allocating. And now another thing, another difference between paging and segmentation is that in the case of the paging, we are dividing the physical memory into frames, whereas in the case of the segmentation, we don't require such kind of differentiation. We don't require, we need to create the partitions in the main memory. So virtual memory is larger than the physical memory. This I had already explained to you. In this figure, what is happening? This is the memory map of my process. Virtual memory. Now we are calling the virtual memory. Now this process is divided into n number of pages. The virtual memory is divided into pages, and this is the memory map for the page, for the process, and this is the physical memory. Few of the pages, they are residing in the physical memory, whereas this is the backing store, and here the whole process is residing. So now we can say that the virtual address space, that is the logical address space, is much larger than my physical address space. The ability to execute a program that is only partially in memory would provide many benefits. What are the benefits? A program would no longer be constrained by the amount of available physical memory. Users would be able to write the programs for a large virtual address space, simplifying the programming task. It is even possible to use more bits for logical address than the bits needed for the addressing the physical memory. Because each user, second point is, because each user program could take less physical memory, so more programs could run at the same time. That is, we are increasing the throughput of the system with a corresponding increase in the CPU utilization and throughput. Another main important point is that less input output would be needed to load or swap each user program, because now instead of, if my program is broken down into 20 pages, so I can start its execution with only 5 pages. So less amount of swapping is required, or memory input output operation is required before starting the execution of a process. So basically, what is demand paging? Demand paging says that bring a page into memory only when it is needed, and therefore in this case, less input output is needed, less memory is required, faster response time is there, and more users can be supported. Page is needed, then we refer to it, and if the reference is invalid, that is, it is not in the domain of a process, then we abort the process. Otherwise, if it is in the logical address space of the process, but it is not in the memory, then we need to bring this page into the memory. So for this particular requirement, here we require a lazy swapper. And what lazy swapper does, it never swaps a page into memory unless the page will be needed. So here the swapper basically deals with the pages, and it is known by the name pager. So now instead of calling it as a swapper, we are calling it as a pager, and what its activity is, page in and page out. So now the question comes, what happens if there is no free frame available? Then in that case, we need to free the space in the main memory. So now the question comes, what happens if there is no free frame available? So for this, we need page replacement algorithms. So what the page replacement algorithm they are doing, they are finding some page in the memory, but they are not in really use. Now this particular thing, it plays a very important role when we are designing a new algorithm, page replacement algorithm. So we generally try to select that victim page, that victim frame in the memory, which is not required for a long time. So for this, we need a good algorithm. So what the performance issue which we are going to address, that the algorithm should result in minimum number of page faults. So some page may be brought into the memory several times due to this logic. So what the page replacement algorithm does, it prevents over allocation of the memory by modifying page fault service routine to include the page replacement. And for this, what we are doing, how we are achieving this, we use a specific bit which is known by the name modify or the dirty bit to reduce the overhead of the page transfer. Now what is happening, once we had selected the victim page, then we are analyzing this particular bit. That is, if that particular page has been updated or not, modified or not. If that particular victim page has not been modified, it implies that the copy on the backing store is same as the copy as that particular page in the memory. So we don't require to page out this page. That is no need for swapping out this page. Now what we will do, we will bring the new page from the backing store onto this particular frame, that is we are overwriting this. But what happens if the modify bit is set, that is the page has been modified, then in that case we will go with the swapping process. So page replacement, it complete the separation between the logical and the physical. Earlier we had seen that the logical address space can be greater than the physical memory space. So how this difference can be, you could say, nullify in the virtual memory concept. It is nullified with the help of the page replacement. That is, large virtual memory can be provided on a smaller physical memory. So basically what we are doing now, we finding the location of a desired page on disk, find a free frame. If there is a free frame, use it. But if there is no free frame, then what is happening? We are calling the page replacement algorithm to select a victim frame. So bring the desired page into the newly free frame, update the page and frame tables, and after this we will start the restart the logic of the process. So basically now what we are doing, in this case, if you look at, we are having two bits, valid and invalid bit associated with my page table. Valid bit says that the page is present in the main memory. Invalid bit means that the page, it means two things. Either the page is not the part of the logical address space of the process, or it is the part but it is not present in the physical memory. Where it is present on the backing store. So if we found the valid bit is I, then in that case what we are doing, we are selecting a victim page. Now this victim needs to be swapped out to the virtual memory, and here the page which we desired, it is swapped in the physical memory. We will update the table, that is we will change the I bit to V bit, and we will change the internal table of the process which is having this particular victim page. And once all the page tables has been updated, we will start the logic of the process. So in the case of the page replacement algorithm, we want the lowest page fault rate. That is the, you could say, performance matrix which we are using in the case of page replacement algorithm. evaluate the algorithm by running on a particular string of memory reference, and this memory reference is known by the name, this string is known by the name reference string, and computing the number of page faults on that string. Now the question comes, how we will get this reference string? Example, we are having a particular process and this size of per page is 100 bytes. So what it says, 0 to 99 instructions, logical instructions, they are residing on page 0. Then 100 to 199, they are residing on page 1. 200 to 299, they are on page 2, and so on. So once we have got the memory references, these are my memory references, I can convert them into number of my page string. 0100, it implies that my page number is 1. So here it comes 1. This is on page 4, this is again on page 1, this is on page number 6, this again 1, again 1, again 1, again 1, this is 6, and this is 1. So how my string got generated? 1, 4, 1, 6. Now what is happening? We are referring this particular page consecutively on different locations, addresses. But once it has been brought into the memory, no matter at which particular memory location you are referring to, that particular page would be count once. So here this number 1 is appearing only once in this case, then 6, and then 1. So this is my reference string which I had got with the help of my memory addresses. So this graph is showing that my number of page faults, it decreases when I allocate more number of frames. Basically, if I am having only 3 frames, then in that case only all the processes, they are using only this much memory. But what if my increase my number of frames to 5, then I am having more space in this case. So basically what the relationship between number of page fault and the number of frames is, it says that as you increases the number of frames, my page fault rate decreases. But it is not always true. We will see later on why it is not always true. Let's start with the very first page replacement algorithm, that is FIFO algorithm, or the first in first out algorithm. What it says, replace that page that has brought initially into the memory. So in this case, I will explain this algorithm with the help of the example. This is my reference string and I am having 3 frames available. So initially I am using pure demand paging, so no page has been allocated so far. So when I need to refer page number 7, it need to brought into the memory. So this is my first page fault. Then with 0, second page fault. With 1, another page fault up to here. But when I refer to page number 2, then in that case it is not present in the memory. So this again lead to another page fault. So I need to select a victim. Now who is going to the victim who has brought into the memory first? So in this case 7 has been brought into the memory first. So we are going to replace 7 with 2. Now for 0, it is present into the memory. So no page fault. In the case of the 3, it is not present into the memory. So we need a victim frame. Who is the victim frame among the 2, 0 and 1? 0 is the first one who has been brought into the memory first among these 3. So we will replace 0 with 3. So this is another page fault. In the case of 0, another page fault. 1 is to be replaced. Next, another page fault. replace 2. Then in the case of the 2, another page fault. 3 has been selected. In the case of 3, another page fault. 0, another page fault. In the case of 3, no page fault. No page fault in the case of 2. When we come on the 1, again there is a page fault, and among 3, which has been brought into the memory first, your 2. So 2 is being replaced with 1. So another page fault, again another page fault. In the case of 0, no page fault. No page fault. In the case of 7, another page fault. So the victim in this case is 0. In the case of 0, another page fault, victim is 1 this times, and in the 1, another victim, again page fault, and 2 is the victim. So total number of page fault is going to be 1, 2, 3, then we are having 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. This is my number of page fault. And how you will calculate the page fault rate? Divide this by total number of frames, that is 3 in this case. So this comes out to be 5. But FIFO, it suffers from a concept, that is a Belady's anomaly. What is Belady's anomaly? Belady's anomaly, it says that if we increase the number of frames, then the page fault don't decrease, but they might increase. Now this particular anomaly, it has been it has given a name, that is a Belady's anomaly, and not all the page replacement algorithm, they suffer from this anomaly, but FIFO algorithm, it suffer from the Belady's anomaly. Another important point to be noted down is that all the reference strings, they don't show the Belady's anomaly. Only a few set of references, with a few set of references strings, the FIFO algorithm, it shows Belady's anomaly. So in this graph, if we look at the graph with the number of frames 1, page fault is 12. When I increase the number of frame to 2, my page fault is still 12. But with the 3, it goes down. Or you could say it is somewhere near about 9. With the 4, again my page fault rate, instead of going down, it is going up. So here the FIFO algorithm, it is exhibiting or showing the Belady's anomaly. With the increase in 5, again there is a drop down, but 6, a constant has been achieved. So if you look at the graph at this particular point, our algorithm, FIFO algorithm, it suffers from Belady's anomaly. Another algorithm, second algorithm, is your optimal algorithm. It is also known by the name opt algorithm. Now what this algorithm does, it replaces the page that will not be used for the longest period of time. That is, it always look into the future. And if a particular page is to be used at a longest period of time, we will select that page as a victim page. Now the important question comes, how do you know this? So theoretically, we are having the formulas to identify this, but when we go for the practical concept, optimal algorithm cannot be implemented. So generally, opt algorithm is being used for the research purposes. It requires future knowledge of the reference string. So basically, it is used for measuring how well your algorithm performs. The same reference string we are referring to with the opt algorithm. First 3 page faults as usual. With the 2, again page fault, but now we need to select among 7, 0 and 1. So if I look, 0 has been referred here, and 1 has been referred here, and 7 has been referred here. So the longest time, if I talk about 7, so my victim page is 7 in this case, it got replaced by 2. With 0, present in memory, no page fault. With 3, again there is a page fault. I have to select among 2, 0 and 1. 0 referred here, 2 referred here, 1 referred here. So the victim page is 1 in this case, replace 1 with 3. 0, no page fault. 4, again there is a page fault. We have to select the victim between among your 2, 0 and 3. 2 referred here, 0 referred here, and 3 referred here. So the victim page is now 0. So we have replaced 0 with 4. Now 2, no page fault. 3, no page fault. 0, again there is a page fault. So we have to select 2, 4 and 3. 2 here, 3 here, and 4 is nowhere. So it is the best choice to replace this. So we have replaced 4 with 0. 3, 2, no page fault. 1, again there is a page fault. Again we need to select a victim between 2, 0 and 3. 2, 0, 3 not referred anywhere. So again this is the best choice. So this is how we can calculate the number of page faults in the case of the opt algorithm. Another important algorithm is least recently used. It is behaving same as opt, but instead of looking into the future, it is looking into the past. That is, replace the page that has not been used for the longest period of time. So this strategy is the optimal page algorithm, looking backward in time rather than forward. So this is my references string. Again, 3 page fault. In the case of 2, again there is a page fault. So I have to select 7, 0 and 1. So among 7, 0 and 1, which is used first? 7, 0. 7 has been used first. So we have replaced 2, no page fault. Again 3, a page fault is there. We have to select the victim among 2, 0 and 1. 0 here, 2 here, 1 here. So we have replaced the 1 in this case. Again, no page fault. In the case of 4, there is again page fault. Victim need to be selected among 2, 0 and 3. 0 here, 2, 3 here, and 2 here. So among these 3, we need to replace 2 according to the LRU Page Replacement Algorithm. So how we are going to implement the least recent LRU Page Replacement Algorithm? The first implementation is with the help of counter. In this case, every page entry has a counter. Every time page is referenced through this entry, copy the clock into the counter. When a page needs to be changed, look at the counter value and determine which are to change. That is, the page with the smallest time value is my victim page. Another important implementation is with the help of a stack. Keep a stack of page numbers in a double linked list form. Page reference, whenever a page is referred, move it on the top. And in this case, my victim page is always at the bottom of my stack. No search is needed in this case for the replacement. So in this case, this is the stack before at point A. Now at point B, I am referring 7 here. This is A and this is B. So 7 is present here, and from here what I have done, I had removed 7 from this position at the top of the stack. And whenever I need to select a victim page, this is the bottom is my victim page. We are having a separate set of LRU approximation algorithm. One is based on the reference bit and another is your second chance algorithm. In the case of the reference bit, what we are doing, we are setting the bit on the page. If we have referred the page, it is 1. If we haven't referred the page, 0. So how I am selecting the victim page with the help of this bit. In the case of the second chance algorithm, the same concept has been deployed, but now what is happening? We are giving a second chance to the algorithm. It is a modified FIFO algo with reference bit. When a page has been selected to be replaced, we inspect its reference bit. If the bit is 0, we replace the page. If the bit is 1, we give it a second chance. When a page gets second chance, then its reference bit is reset to 0 and its arrival time is reset to current time. A page that is given a second chance will not be replaced until all other pages in my queue are replaced or given second chances. So here I have maintained a circular queue of all these pages. This is my pointer location. Here the reference bit is 1, so I will move to this and convert this to 0. Again, I will convert to 0, and when I am reaching here, the reference bit is 0. So now this is my victim page. Another set of algorithms, page replacement algorithms, they are known by the name counting algorithm. Here we keep a counter of the number of references that have been made to each page. There are two set of algorithms, one is LFU and another one is MFU. LFU, it replaces the page with the smallest count, whereas MFU, it replaces the page with the highest count. And why? Because it is based on the argument that the page with the smallest count was probably just brought in and has yet to be used. So this is all about for today. These are the references which have been referred while preparing the slide. Thank you and Jai.